A nuclear plant contains some of the most advanced control and safety systems due to its hazardous failure potential. Here's a light water nuclear reactor design that is adopted in the Fukushima Daiichi power plant. So, how does it actually work? The reactor vessel contains a nuclear core where nuclear fission reactions occur, generating an enormous amount of heat to produce steam. The reaction is controlled using control rods. The steam then travels to a turbine and drives it. Subsequently, the turbine shaft drives the generator, producing electricity. The resulting steam then goes through a condenser, which is cooled with nearby seawater. The variable speed pump controls the seawater flow rate while the filter ensures that the cooling water is free from contaminants. The condensed primary water then goes through a demineralizer to remove any impurities. Lastly, the water is preheated before returning back to the reactor vessel for a better temperature control over the reactor core. So, with this well-established design, what sort of failure can be anticipated? Imagine one day, the reactor temperature spikes. The cooling water flow rate is increased to remove this excess heat. Without monitoring the composition of water, a large amount of chloride ions pass through the filter, causing the filter to be weakened and physically damaged over time. At the time of the event, the filter system malfunctions without warning, allowing free passage for the contaminants into the cooling water stream. In the presence of chloride ions and stresses, local stress corrosion cracking happens at the tube wall, causing leakage. The contaminant gets into the tube and travels in the primary loop. Manual composition analysis is carried out once every week, at the demineralizer unit, so there was no detection of a failed unit at the time of the event. Subsequently, the contaminants deposit on the surfaces of the reactor core and control rods. Ineffective heat transfer causes more nuclear fission required to maintain constant outlet steam temperature. The control rods are slowly regulated out of the system and the core temperature increases. When the temperature alarm high sounds, the operator notices a tremendous increase in the reactor temperature. The operator attempts to regulate the maximum flow of cooling water into the reactor, but the temperature refuses to drop. Then, the operator attempts to shut down the reactor, but the control rods are unable to re-immerse to the core due to fouling-induced mechanical failure of the control rod's mechanism. Soon, the runaway reaction causes all the water to evaporate. The pressure of reactor builds up and eventually explodes. So, how can we actually prevent this disaster from happening? Firstly, to address the filter malfunction, a spare filter can be installed with an automatic safety interlock system. A simple composition feedback controller is also installed to constantly monitor the cooling water composition. Whenever the water exit composition of the normal operating filter is undesirable, the interlock system automatically switches to the spare filter so that the normal filter can undergo maintenance. Secondly, the temperature spike could be regulated or prevented by using a more advanced control system, which can consist of a cascade plus feedforward control system. The cascade measures the disturbances in the cooling water while the feedforward provides a more predictive control over the primary water temperature. This will allow for more stable operation and reduces the likelihood of temperature spikes. Last but not least, a composition analyzer can be installed after the demineralizer to constantly monitor its exit flow composition. This helps to ensure that the unit is operating normally at all times and can warn the operator to act preemptively to change the exhausted ion exchange resins. In summation, here's an overview of the safety layer. With this, the overall safety of the plant will be more resilient. As a conclusion, let's compare the key differences between the actual Fukushima and theoretical disasters. Firstly, for the Fukushima incident, the catastrophe was due to an earthquake that was followed by a tsunami. The earthquake caused the off-site power to be lost while the tsunami disabled the emergency diesel generators. This led to the malfunction of the water cooling system. Despite the insertion of control rods, the excess decay heat could not be removed due to malfunction of the water cooling system. Then, for our B6 reactor accident, the catastrophe was due to the malfunction of seawater filter that caused stress corrosion cracking to occur in the condenser tubes. This caused the contaminants to accumulate in the reactor vessel, which caused ineffective heat transfer and withdrawal of control rods from the nuclear core. Lastly, the containment attempts were nullified as higher cooling seawater flow rate induced more fouling and caused the insertion mechanism of control rods to fail.